Beam offset. Light is incident in air at an angle theta sub A, as you can see in the figure, on the upper surface of a transparent plate. So that interface, transparent plate and air interface, I called A. The surfaces of the plate being plane and parallel to each other. So this plane, the bottom plane and top plane are parallel to each other. Prove that theta sub A is equal to theta sub A prime. So that's the angle of incidence on the top surface, upper surface, and that's the angle with which the beam emerges from the bottom surface. That's theta A prime with respect to the normal. Part B, show that this is true for any number of different parallel plates. So if I have more parallel plates, it would be the same result. Part C, prove that the lateral displacement D of the emergent beam is given by the relationship. So as you can see, this beam, incoming beam, has an offset that's by an amount D as it emerges from the other side of the plate. So that is given by T, the thickness of this plate, multiplied with sine theta A minus theta prime B. What is theta prime B? That is the angle of refraction in the material, divided by cosine theta prime B, where T is the thickness of the plate. Part D, a ray of light is incident at an angle of 66 degrees, so that means theta A is 66 degrees, on one surface of a glass plate, 2.4 centimeters thick, that's T, with an index of refraction of 1.8. The medium on either side of the plate is air. Find the lateral displacement between the incident and emergent rays, so that's the amount of offset we're trying to calculate. So let's start with proving that theta A is equal to theta A prime. So what I'm going to do is write Snell's law of refraction, Snell's law, at interface A. So that's the top surface. Now we're coming from a medium with index of refraction n at an angle theta A with respect to the normal. So that would be n sine theta A, theta sub A, must be equal to the angle of refraction theta prime B, so n prime sine theta prime B. N prime is the index of refraction of the transparent material. And if you look at theta B and theta prime B, so this is, since these two planes are parallel, theta B and theta prime B, you can see in the figure, are equal to each other. So I know that theta B, theta sub B, and theta prime sub B are the same because we have parallel flat surfaces at these interfaces, bottom and top surface. Now I'm going to write Snell's law of refraction at interface B. So for this interface, we're approaching the bottom surface with an angle theta B with respect to normal and refracting with angle theta prime A in the medium with index of refraction n. So we have n prime sine theta prime B is equal to n prime sine theta B, because theta prime B and theta B are the same, and that must be equal to n sine theta prime A. So that is basically this angle. All right, so here I'm writing Snell's law for this interface. N prime sine theta prime B is n sine theta prime A, but theta prime B is theta B, so it's n prime sine theta B is equal to n sine theta prime A. And since we have, by combining these two equations, n sine theta A equals n prime sine theta prime B equals n sine theta A prime. So we have n sine theta A is equal to n sine theta prime A, which is true because they're both equal to n prime sine theta prime B. So we can say that theta sub A must be equal to theta sub theta prime A. So this will be equal to theta prime A. That's what we were asked to show in part A. Now, if we generalize this to the case where we have many parallel flat surfaces, let's say that if we add another interface C, then we would have n sine theta A, the law of refraction, giving us n prime sine theta prime B, giving us n prime sine theta B because it's the same angle on two sides. This would be equal to n double prime sine theta prime C, which would be equal to n double prime sine theta C, which is the same thing as n sine theta A. Therefore, this continues if I add more interfaces. Theta prime B is theta B, theta prime C is theta C, etc. for all parallel flat surfaces. Therefore, we can conclude that theta A must be equal to theta prime A. So at outside we have n sine theta prime A, and this is true regardless of the number of parallel plates. All right, so we reached the conclusion that the angle theta A is equal to theta prime A for any number of different parallel plates, because we keep writing the same equation, and sine theta A finally turns out to be n sine theta prime A. Regardless of the number of intermediate steps here, we always have theta is equal to theta prime A. Part C, we want to find the offsets. Okay, so let's take a look at this geometry here. So here is the incoming wave. Incoming wave makes an angle theta A with respect to the normal in the medium with index of refraction n. And then we have this angle theta prime B for angle of refraction, and it comes out with an angle theta prime A on the other side. You can see that this ray is parallel to the incoming ray. Therefore, this angle here will be equal to theta prime A minus theta prime B. So this is, since theta A we have shown to be equal to theta prime A, this is theta A minus theta prime B. So this angle is theta A minus theta prime B. So if I look at this triangle, ABP triangle, which is a right triangle, so let's look at the ABP triangle. If I write the cosine of theta prime B, you can see that it will be equal to T divided by the length of AP. So this is T divided by AP, and therefore I can see that the length AP is T divided by cosine theta prime B. On the other hand, if I concentrate on the APQ triangle, so that is APQ triangle, which is also a right triangle. Here I have one angle, theta A minus theta prime B. Sine of theta A minus theta prime B would be equal to the offset D divided by the length AP. So that is D divided by the length AP. So this gives me, for AP, D divided by sine theta A minus theta prime B. So by equating these two, the thickness T divided by cosine theta prime B, length of AP, is equal to the offset distance D divided by sine of theta sub A minus theta prime B. I can see that they're both equal to the length AP. I can see that the offset distance is T multiplied by sine theta sub A minus theta prime B divided by cosine theta prime B, which is what we were supposed to show. T sine theta A minus theta prime B divided by cosine theta prime B. Now we're going to plug in some numbers here in part D. So if the angle of incidence theta sub A is 66 degrees, the thickness is 2.4 centimeters, index of refraction of the material is 1.8. If I write Snell's law of refraction, I have, coming from air, index of refraction 1 sine 66 equal to 1.8 sine theta prime B, angle of refraction. This gives me theta prime B is equal to sine inverse sine 66 divided by 1.8. Sine 66 degrees divided by 1.8. And if you calculate, this angle is equal to 30.5 degrees. Therefore, if I substitute this into my offset formula, D is equal to 2.4 centimeters multiplied with sine theta A 66 degrees minus theta prime B 30.5 degrees divided by cosine theta prime B, cosine 30.5 degrees. This gives me D is equal to 1.62 centimeters. So that's the total amount of offset in the beam direction. Okay, so we have a beam offset problem. A beam enters a coming from a medium with index of refraction and to a transparent material with index of refraction. N prime thickness is T. The angle of refraction is theta prime B, which is equal to theta B, which is the angle of incidence on the lower surface. Theta prime A is the angle with which it emerges from the bottom surface. And we want to show theta is equal to theta prime A, and then we want to calculate this offset. So first of all, writing Snell's law at interface A, n sine theta A is n prime sine theta prime B. We see that we obtain this formula, and theta sub B is equal to theta prime sub B. Why? Because we have flat parallel surfaces, so these two angles should be the same. They're two parallels. And Snell's law at interface B is n prime sine theta B is equal to n sine theta prime A. So n prime sine theta B is the same thing as n prime sine theta prime B, because the angles are the same, and sine theta A prime. But n prime sine theta prime B was also equal to n sine theta A. So this is theta prime B. Therefore n sine theta A equals n sine theta prime A, theta A equals theta prime A. If we insert another interface, then we would have an intermediate, n double prime sine theta prime C equals n double prime sine theta C. So we would have the same scenario that's happening here in the other material with index of refraction n double prime here. So we would see these intermediate equations would not change the end result. Theta prime B is theta B, theta prime C is theta C, etc. So for all parallel surfaces, finally we would find n sine theta prime A is equal to n sine theta A. So the angle with which it's incident and the angle with which it emerges are the same, regardless of the number of parallel plates. The amount of offset can be calculated by considering these two right triangles ABP and AQP. If you write the length of AP in terms of cosine of theta prime B and sine of theta A minus theta prime B. Why theta A? Because this angle and this angle are the same, because these are two parallel rays. And theta prime A is the same thing as theta A. So this is theta prime A minus theta prime B, or theta A minus theta prime B. So cosine of theta prime B is T divided by AP. Cosine of theta A minus theta prime B is sine of theta A minus theta prime B is D divided by AP. So this gives us the offset. The amount of offset, we calculate the lateral displacement of the emergent beam to be T sine theta A minus theta prime B divided by cosine theta prime B. Now, if we have an angle of incidence 66 degrees, thickness 2.4 centimeters, index of refraction 1.8, Snell's law tells us that theta prime B must be 30.5 degrees. So theta A minus theta prime B and theta prime B in the formula 2.4 times this ratio gives us 1.62 centimeters for the lateral displacement of the beam.